In this lesson, we will discuss hypothesis tests for population mean when the standard deviation is unknown. We first begin and check a few quick assumptions. Verify you have a simple random sample. The sample size should be large, greater than 30, or our population is approximately normal. If both of these are met, then we can go forward to our steps to perform the hypothesis test. Step 1 is to state the null and alternate hypothesis. As before, we have left-tailed, right-tailed, and two-tailed alternate hypotheses. Then you choose a significant level alpha if it's not already given, and find the critical value or values. Use n-1 degrees of freedom, where n is a sample size, and the chart critical values for students' t-distribution, which is given in the next few pages. Then compute the test statistic, x bar minus mu naught, divided by our sample standard deviation divided by the square root of n. And then we reject h naught based on the following things. For a left-tailed test, we reject if our found value of t is less than or equal to our critical value. For a right-tailed, we reject if our found value of t is greater than or equal to our critical value. And for our two-tailed, we reject if our value of t is greater than the positive or less than the negative. Visually, what does this look like in our normal distribution charts? So in this case, if we had a left-tailed test, we would reject if our test statistic had us in this left tail of the critical value. And if it was a right-tailed test, we would reject if our test statistic was in this right tail. And then if it was two-tailed, we would reject if we were before the left tail or after the right tail. If we're not in either of these sections for the given test, we would fail to reject. Finally, we state our conclusion. Now, this is a chart that we've seen before in previous lessons, but as we're going to use it in this lesson, I have included it again here in our notes just so it's an easy reference. So we have our critical value for the student's t-distribution, and we know how to read this. We've got our degrees of freedom, the area to the right portion of the tail. So in this example, we're asked to find the critical values or values for the significance level alpha that's given, sample size n, and alternate hypothesis h1. So in this one, our alpha is 0.05, n is 39, h1 is that mu should be greater than mu naught. From this, I immediately need to write down that this is right-tailed because that will impact how I draw what's going on. So for my right-tailed graph, I draw my normal distribution, and I want to know what is this critical value here that I'll then judge my test statistic based off of. Now we know for the t-test, we have something called degrees of freedom, and the degrees of freedom is the sample size minus 1. So here my degrees of freedom is 38. Now looking back at our chart, we can see for a right-tailed hypothesis test, the area to the right is equal to our significance level alpha. So this area is 0.05. Now on the left side of the screen, I've brought up the chart so we can see both at the same time. I'm going to look for the area right of the tail to be 0.05. That's this column. Specifically for 38 degrees of freedom, that is the value 1.686, so that is my critical value here. T alpha equals 1.686. So remember, whenever you're dealing with the hypothesis test for a population mean when the standard deviation is unknown, we first figure out is it left, right, or two-tailed. That distinguishes how we draw this. And then we know for left and right-tailed, the area to the left or right, respectively, is the alpha level. For a two-tailed test, the area to the left and right is alpha over 2 because we split that alpha value into two different branches. So for our next example, we see alpha is 0.01, n is 34, and then based on how we would phrase this, mu is less than or equal to mu naught, we know this is a left-tailed. test. So as I draw my normal distribution sketch, try to make it look a bit more symmetric. I've got some T alpha value that I need to find, but I know the area to the left of that is 0.01. My degrees of freedom is equal to 34 minus 1, which is 33. And now we need to turn our attention to the chart. So the way this chart works is it gives us area to the right of the tail. But we know by symmetry, if I had some value that had area to the right as 0.01, then this value would just be the negative version of that. So I could look and see what, area to the right has a value of 0.01, and then just put a negative there to show that that's actually the value to the left. So I look at the 0.01 column. We have 33 degrees of freedom. And the value would be 2.445 if the area to the right was 0.01. However, we know we're looking at the symmetrically opposite value. It's the area to the left. So I'm going to mark that as negative 2.445. So keep that in mind. Whenever you're dealing with left-tailed test, you can still figure it out from this table. However, the table directly helps you find the right-tailed test initially. So you just negate it to get the left-tailed version. Now we'll go through C together, and then I'll ask you to pause the video and attempt D on your own. Reading through this, we have alpha is 0.10, N is 6, and our H1, or alternate hypothesis, is mu can't be equal to mu naught. Now we quickly recognize this as a two-tailed. So I draw my sketch. Now this alpha, since I've got two tail, the area is split symmetric or equally between two regions, area before, area after. So if I have to distribute this 0.1 into two regions, that gives me that both regions has an area of 0.05. And specifically, whatever this T alpha over 2 is, then this will just be negative T alpha over 2. So we can quickly find both of these from our chart. We record our degrees of freedom as 5 because our sample size is 6. Okay, so we're going to find the area right of 0.05, and then I'll just negate it for the portion on the other side. So here's our column for 0.05, area to the right, our row for 5, and we see the value is 2.015, and this would be negative 2.015. So in this case, I have two critical values because it's a two-tailed test. Now, I would encourage you to pause this video and attempt this last problem on your own, and then unpause to check your work. So here for our, again, two-tailed test, I remark on that. We draw our sketch of a normal curve. We know that we're dealing with two tails. And the area that we split between these two tails is 0.05. So if I have 0.05 split into two different sections, each section gets a smaller value of 0.025. So I'll record that in my sketch. This area is 0.025. This area is also 0.025. My degrees of freedom is 1 less than the sample size, so 25 minus 1 is 24. We've got enough information that we now go to our chart. So we've got our 0.0 025 area column, cross that with the fact that we've got 24 degrees of freedom. And that gives me my critical value of 2.064 for the positive version, and then negate that for the symmetric value across the peak, negative 2.064. Now in this last example, we practice finding the critical value and values, depending on different test setups. Now let's go through the whole problem, and as you have yours for your reference, I might turn your pages back to our initial steps for this hypothesis test, and you can just follow along piece by piece. So we read that the mean annual tuition and fees for a sample of 14 private colleges in California was $37,900, with a sample standard deviation of 7,200. We are told the population is approximately normal. Can we conclude that the mean tuition for the fees for private institution in California differs from 35,000? So remember that phrase differs from is not equal to. Use alpha equal to 0.001 level of significance. Now side by side, we've got our steps here. So first step that we need to do is state the null and alternate hypotheses. So we want to figure out if the mean tuition and fees is different than 35,000. So let's let our null hypothesis be that it's the same to 35,000. And then our alternate hypothesis is that it's not that value, that it differs. With that, we've done step 1. Okay. Now, step 2 said choose a significance level. We don't need to choose it. It was already given to us. Alpha is 0.01. And now we need to find our critical value. We know this is a two-tailed test. So if I was to visualize this here, I'd have my normal distribution. Got my two tails. Now we know my alpha of 0.01 in a two-tailed means that that area is split in two places. So each portion gets 0.005 of area. And this we know helps us with our student's t distribution chart to find the critical values. So we'll go to our chart now. Okay, we've got our column for 0.005. Now we had 14 colleges, so my degrees of freedom is 14 minus 1, or 13. So our area here is, our critical value, the positive version is 3.012, the negative version is negative 3.012. So we now have our critical values. So step 2 is accomplished. It now says step 3 is compute the test statistic. So I'm going to say T is x bar minus my mu naught over S over the square root of the sample size. Now my x bar was that the sample mean was 37,900 minus a mu naught of 35,000 divided by our sample standard deviation of 7,200 divided by the square root of 14. Now remember, when you're using n, you go back to the original sample size, not the degrees of freedom. Now we will calculate this. Since we want to compare it to our critical value, which has 3 decimal places, all of the students' t distributions have 3 decimal places, we will want to round this to 3 decimals. When we type this into our calculator and round, we will get 1.507. Okay, now keep in mind, our 1.507 is here in this middle region. But in a two-tailed test, it says you reject the hypothesis if your t value is in this positive region greater than the positive test or critical value, or in this previous region before the negative critical value. However, our test statistic is somewhere about here. So in this case, we would fail to reject or do not reject. And we know when we fail to reject, all we can say is there's not enough evidence to conclude that whatever we were looking for occurs. So let's phrase that in terms of this problem. So I begin with there is not enough evidence to conclude that, and then what were we trying to conclude? That the mean tuition and fees for private institutions in California differed from $35,000. So, as always, if you have questions, please reach out to me via our campus communication, and I'll be very happy to help you.